Hi, I'm Dan Harris. I'm a principal software engineer at CoreLogics, and today I'm going to be talking about cost-effective burst scaling for distributed query execution. So my day job at CoreLogics is building the rather unimaginatively named Data Prime query engine. So this is a distributed query engine for doing low-cost, real-time analytics on observability data. Aside from that, I'm a committer on the Apache Arrow project, mostly focusing on the Arrow implementation of Rust, the Rust Arrow implementation, Arrow Data Fusion, and Arrow Ballista. And the one thing I've learned over the past couple of years is that a query engine is sort of defined by its P99 latency, unfortunately for me and my team. All right, so this talk isn't really focused on the query engine specifically, but it's worthwhile to create some context around why autoscaling is important for us. And so the goals that we set out for when we designed this is, one, we want a native execution layer for a custom query language we designed for dealing with heterogeneous semi-structured data called Data Prime. And this isn't a general analytics engine where we're running huge batch jobs where latency isn't super important. This is meant to drive sort of low latency, real time, interactive queries from our customers over petabytes of data that have been ingested into our platform. And we're also looking to build something that's highly cost effective so we can sort of offer a cheaper solution to our customers. So, with that in mind, we designed around separation of compute and storage. That is, we want to store the actual raw data in cheap object storage and have a sort of scalable compute layer that we can use to execute queries. And that really allows us to efficiently utilize infrastructure resources so that we can sort of keep the compute costs on our side down and offer sort of better product for customers. So again, the architecture of the engine could be a talk in its own right, but not this talk. So I'll just say briefly that Data Prime Query Engine is based off a heavily customized fork of the open source Arrow Ballista project, which itself is a distributed execution engine for Arrow Data Fusion, which is a query execution engine based on Apache Arrow. And there's sort of two component services. In practice, it's a lot more complicated, but for our purposes here, there's a scheduler, which is sort of an orchestration layer. So it's going to be responsible for distributed query planning and orchestrating execution. And there are executors, which are the actual workers in the system. So they're sort of the dumb executors that just take a task from the scheduler and execute it. So the scheduler doesn't have to be particularly scalable, but the executors do, since the query latency is sort of limited by our executor compute capacity. All right, so we're going to go through a little bit of like a dialectic on autoscaling here. So first, why do we want to autoscale at all? So one, customer workloads are pretty predictable, right? We build tools for developers. They work normal-ish business hours in any given region. So our sort of query load varies somewhat predictably over the course of a day. Query execution can be very effectively parallelized. So we can run even very large queries in a relatively short period of time by parallelizing and sort of separating the query workload out across lots of machines. And the fact that we've designed with the separation of compute and storage means that we can scale up and down very effectively. We don't have to move data around to add more compute capacity to the system. All right, but it's not all sunshine and roses, right? So some of the wrenches in the system are that, we talk about overall query capacity, but we can also get individual queries that are extremely large. So it's not that uncommon for us to see queries that need to scan 500 terabytes of data, and that's for a single query. So that makes it extremely challenging to sort of scale up to execute that query, because scaling up takes time to provision new machines and bring them online. So by the time you scale up, the query is either already timed out or it's already done. And that's mainly because auto-scaling signals are laggy, right? You don't have like a real-time view of the system. You have metrics that are lagging by anywhere from 30 seconds to a few minutes. And of course, servers are expensive, so you can always just keep a ton of compute capacity around at all times, but then you're paying for that. You're paying for a bunch of servers that are sitting around at, close to zero utilization. All right, so how do we synthesize this? So really, we can think about this as two sort of distinct subproblems. Problem one is, how do we keep enough spare capacity so that we can manage sudden bursts and requirements without, falling over or providing a really slow experience for our users? And the other problem is, how do we handle sustained load in a cost-effective way, right? So we want to provide a good experience, but we also want to do it at a reasonable cost to us and our customers. And the nice thing about sort of decomposing the problem into subproblems is we can look at each of those problems and we can apply different tools and technologies to each one. So for problem one, we have AWS Lambda, or serverless computing more generally if you're on a different cloud provider. So this is nice because it gives us instant-ish availability, right? That capacity is there at all times, and you don't need to provision new infrastructure to use it. And you only pay for it when you use it, right? So you're not paying anything to have that capacity around. You're only paying for it if you actually need it. But it's really, really expensive. So I think Lambda per compute second is about 12 times the cost of EC2. So you want to use it when you absolutely need it, but if you have sustained load, it's really, really cost inefficient way to do compute in AWS. And for problem two, we have, good old AWS EC2, right? Just regular old server VMs. So they're not a good solution for problem one because it takes time to spin up new machines. And you pay for it whether you use it or not. So if you keep that spare capacity around just in case, you're again paying for servers that are doing nothing. But when you are using it, it's relatively cheap, especially compared to Lambda. All right. So the sort of shape of the solution is kind of clear, right? We need to be able to, in so many words, dynamically execute between AWS Lambda and EC2. And so to explain somewhat briefly how we do that, we're going to take a brief digression into how do you do distributed query execution to begin with. So on the top here, we have a data prime query in our custom language. And then under that, for those not familiar with data prime, the sort of equivalent SQL query. So what any database engine is going to do is going to parse your query, and then it's going to turn that text query into an execution an execution plan. And the execution plan is actually what's going to be executed by the database engine. And so the execution plan both sort of describes what the engine is going to have to do to execute that query, and also bakes in the way in which that work is parallelized across, on a single node, it would be multiple cores, but in a distributed environment, multiple machines. So in this case, we have a fairly simple plan, right? We're going to scan the underlying table. Just for the sake of argument, let's say we want to break that scan into 1,000 partitions. We're going to project the columns that we need. Within each one of those 1,000 partitions, we're going to do the partial aggregation that we want to do in the final result. But then we need to repartition by coalescing all of those 1,000 partitions together. And then finally, we do a final aggregation to get our final query result. And so that's the sort of single node execution plan, because you can do these repartitionings with shared memory, right? Each one of these partitions would, conceptually be running on a separate operating system thread, and we can just shuffle memory between them. So to turn that into a distributed plan, it's actually pretty conceptually simple, right? You obviously don't have shared memory between different machines, but we do have networks, right? So we can basically, we can take our single node plan and we can chop it into stages, and we chop it at every point that we have some sort of repartition operation. So in this example, we have a single repartition, so we can create a distributed plan with two stages. One that executes that partial aggregation on each partition, and that can be spread out over 1,000 machines and done completely in parallel. And then a final stage in which we grab the results from each one of those 1,000 input tasks, and we do the final aggregation. And so how this is typically orchestrated in our execution model is the scheduler will sort of get the query and it'll create that two-stage execution plan. And then it will orchestrate the task execution among the executors. So in this case, we have two stages. Stage 2 needs to run after stage 1. So the scheduler will distribute those 1,000 partition tasks to, executors as they're available. Once those are finished, then it can schedule stage 2 on a different executor. And when it does that, it can basically tell that executor where to grab its input partitions from all its child stages. So when this stage 2 task runs, what the first thing it's going to do is going to go fetch its inputs from the other executors that executed the stage 1 tasks. So you can sort of immediately see where this is problematic for executing on Lambda, right? Because while you can, in theory, do the shuffle as just a purely network operation, in practice, it's really not practical to schedule this entire sort of execution graph all at one time, because the overall plan might require 10, 20, 30,000 partitions. So you don't have all of those resources available at any given time. So you have to sort of do it in chunks, which means that the output from tasks needs to be stored somewhere, while the task that's going to consume its output is scheduled by the scheduler. So, and Ballista and DataPrime Query Engine, what that means is we essentially write the output from the output from tasks to the local disk on the executor in Arrow IPC format. And then that can be fetched using the Arrow Flake protocol for sort of downstream stages that are depending on it. So obviously in Lambda, it's ephemeral. You don't have a disk. You can't go grab it from, go grab the data from a Lambda function. So we have to modify this model for this sort of hybrid execution. So instead of the scheduler dispatching these tasks to Lambda functions directly, we have to have this sort of proxy layer in between. And so this is an executor that has the special role of basically just dispatching tasks to Lambda functions. And this can actually be sort of transparent to the scheduler. The executor can do this on its own without the scheduler having to necessarily know whether a task it's sending to the executor is going to be executed on Lambda or on EC2. So what this does is the executor will basically get the task from the scheduler, and then it's going to take that task and it's going to dispatch it to a Lambda function. The Lambda function is going to actually execute the plan, and then it's going to push the results using the Aeroflight protocol back to the executor, which is going to then save it to local disk, the same as if it had executed the task locally. And then the stage 2 executor can just fetch the partition from the stage 1 executor, and it's sort of everything is transparent to the rest of the system, and works the exact same way whether the task was executed locally or not. And because this is, we still have the executor, we still require that physical infrastructure for this executor that does the dispatch. But because it's not doing heavy CPU work, we can get much higher concurrency. So whereas a EC2 executor can execute maybe 30 tasks concurrently locally, the Lambda executor can handle many hundreds or thousands of Lambda tasks. So we get a lot of concurrency in the system with relatively little EC2 infrastructure there. All right. So that's sort of in general how we actually orchestrate this hybrid execution. But we still have to kind of figure out what are our signals for autoscaling? When do we actually autoscale? And sort of how do we orchestrate that? So you can sort of try this a couple of different ways, right? So you can just look at something like CPU utilization. But this is, I mean, honestly, it's always a bad auto-scaling metric. We should stop using it in general. But in our particular case, the scheduler is sort of managing the task concurrency on the executors. So if we're doing things right, CPU utilization should be always high on the executors and should never get overloaded. So we can't really use that as an auto-scaling signal. The scheduler will have like a task queue, right? So it gets jobs, it does the plan, it breaks that into tasks. It's got a queue of tasks, which it's parceling out to executors when they become available. So the length of that queue seems like it would be like a natural signal for auto scaling. And while conceptually that makes sense, it's in practice it doesn't work that well. So the basic problem is that when we talk about auto-scaling signals, we're typically talking about some sort of sampled metric, right? So you're using something like Prometheus. Metrics are being scraped every 15, 30 seconds, however you have it configured. So the size of the task queue can be quite volatile and sampled. And so even when you try and smooth it, you get sort of too much volatility to be a really high fidelity signal. So we finally settled on something we call task load average. So this is very similar to the sort of CPU load average you might see if you're looking at trying to see how hard a server is working. It's basically taking the over a given time period, the average the number of task slots on executors that are occupied divided by the total number of task slots. So this gives you a value between 0 and 1 for basically how many task slots are being used at any given time. Because tasks last for anywhere from 1 to 30 seconds, you get a relatively accurate value even when you sample it. And most importantly, if we take the smooth value, right, so we take like the 15-minute trailing average of the instantaneous load average, we get a really good metric for like sustained load. So that is, we're looking at the load that is sustained over a long period of time, in which case it makes sense to start shifting that load to EC2. All right, so putting that all together, right, we sort of have our 4-point plan here, right? So one, you have to architect for this hybrid execution model where you can dynamically shift work between serverless execution and EC2. You first spiky compute loads onto serverless workers, which are always there and always on, but very expensive. And then as you start to see sustained load, you start to shift that work to much cheaper EC2 compute. and then we all profit. All right. And as a sort of final coda here, this is from one of our internal dashboards. And so the green line here is the number of tasks being executed on Lambda, and the yellow is number of tasks being executed on EC2. And what you can see here is a very sort of fallow period in which we're not doing much at all. And then as queries start to come in, at, say, the start of business, the green line goes up as we sort of push that initial work onto Lambda. And then as things really start to get going in earnest, we start to scale up the EC2. And so you can see by the end of this graph, when we're kind of in the middle of the day, the vast majority of the compute's being done on EC2 instead of Lambda. So we're getting a much more sort of efficient cost balance between our infrastructure. All right, cool. That's it. So happy to connect if you want to say hi. So you can reach me at my email or on Twitter or X or whatever we're calling it these days. I'm at ThinkHarderDev, and then on GitHub and LinkedIn. Thanks, everyone.